Welcome to this explainer on load-sharing methodologies, specifically looking at speed droop versus isochronous control. We're jumping right in today to unpack the critical engineering strategies that stop massive marine generators from literally fighting each other for control of the grid. If you've ever wondered how these massive shipboard power plants keep multiple prime movers perfectly synced without tearing the whole system apart, well, you're in the right place. Okay, so let's set the scene. Picture this. You spin up two massive marine generators and connect them in parallel on a single bus bar, but you don't actually give them a designated load-sharing strategy. What happens? Do they just play nice and naturally split the work 50-50? Absolutely not. Without a specific control philosophy in place, they're going to engage in a constant, invisible, and honestly highly destructive tug-of-war. Because instead of cooperating, one of those generators will violently hog the active load, pulling as hard as it can and maxing out its fuel rack. Meanwhile, the other generator just kind of coasts along, doing absolutely zero useful work. It's a wildly unstable situation that leads straight to tripped breakers and ship-wide blackouts. And that is exactly why two proven load-sharing methods exist to decisively stop that fight before it ever even starts.
Let's look at Method 1, Speed Droop Control Methodology. This is a brilliant, super rugged engineering philosophy. It basically intentionally yields just a little bit of ground to maintain overall independence and stability across the entire power plant. Think about it like picking up a heavy weight. Your body naturally braces and slows down slightly, right? Well, a generator does the exact same thing. Speed droop control intentionally lets the engine speed drop just slightly as the mechanical load increases. So as the load rises, the governor's speed reference dynamically decreases. By allowing this slight sag in speed, multiple generators can naturally balance their active power output against one another. If one starts taking on too much load, its speed sags a bit more, naturally shedding that excess load right back to the other machine.
Now, check out the math here, because it's actually incredibly elegant. The formula for droop, represented here by ds, is a beautifully simple proportional relationship. It's simply the ratio of the no-load speed minus the nominal speed, all divided by the nominal speed. You just set this curve in the governor, and the actual physics of the engine take care of the rest. And that formula brilliantly illustrates the absolute biggest advantage of speed droop. This dynamic, continuous correction works with zero communication links between the engine governors. Like, literally none. You don't need a single data cable passing load percentages between generator 1 and generator 2. The physical drop in speed is the only feedback the system needs to share the active power evenly.
Moving on to Method 2, Isochronous Speed Control. So this brings us to a completely opposing philosophy. Where droop yields, isochronous stands completely rigid. It's the exact opposite approach. In isochronous mode, the frequency stays perfectly flat at exactly 50 or 60 Hz, no matter how violently the electrical load is fluctuating on the network. But, and this is a massive but, to achieve that unwavering precision, it demands active load-sharing communication links between every single engine governor on the board. The system has to continuously calculate the network's average per-unit load over a data cable, and then actively adjust every single fuel rack to match that exact mathematical average.
Let's put this into practice with the mid-voyage comps failure test.
Now that we have the theory laid out, let's test how these two philosophies handle a high-stakes marine emergency. This is where the engineering really meets the reality of the ocean. Imagine you're in heavy seas, the vessel is pitching hard, and suddenly, bam, your inner governor communication cable snaps mid-voyage. The data link is totally gone. Which load-sharing mode keeps sharing active power correctly without skipping a beat? Droop or isochronous?
If you guessed droop, you hit the nail on the head. Because it needs absolutely no communication link at all between the governors, a cable failure doesn't even touch its ability to function. The physical speed drop of the engine is the only signal it relies on, and, well, you can't break physics. Isochronous mode, on the other hand, it loses its load-sharing coordination the exact instant that data link drops. Without that constant stream of average load data, the isochronous generators will immediately start fighting each other for the load, just like we talked about at the very beginning of this explainer.
All right, let's hit the summary and next steps.
So, to wrap this up, you now understand the core differences between these two foundational active power load-sharing strategies. They are literally the bedrock of how we keep marine grids stable. Speed droop gives you that rugged, communication-free stability by letting the frequency yield just a little bit. It's essentially bulletproof.
Isochronous control gives you rigid, unwavering frequency precision, for sure, but you're paying for that precision with a severe vulnerability to data link failures.
Which leaves us with a critical, really provocative question to explore next time. If speed droop alone guarantees survival and stability without relying on a single data cable, why do modern vessels still absolutely demand a master power management system, a PMS, sitting above it all? How exactly do we handle reactive power with voltage droop, and how does the PMS act as the ultimate orchestra conductor? Think about that, and we will unpack the whole shebang in Part 2.